Moving on, Module 6, Stoichiometry. We're going to cover the first half of Module 6. We're going to go up to example 6.5. A lot of information in this module. Mole relationships in chemical equations, limiting reactants and excess components, fully analyzing chemical equations, relating products to reactants in chemical equations, using chemical equations when the limiting reactant is identified, volume relationship for gases in chemical equations, empirical and molecular formulas, and then more complicated experiments for determining chemical formulas. A lot of information, but we're going to take everything one step at a time. So let's define stoichiometry. What are we learning here? Well, stoichiometry is the mathematics of chemical equations. So all the math that we can do with a chemical equation, remember that a chemical equation is a recipe. So everything we can do mathematically with it is stoichiometry. Computing how much of a reactant you need to make so much of a product. If you have so much of a product, how many grams of a reactant do you need, a specific reactant, and so on. All of the combinations that you can think about that you can use to find out reactants, products, and so on is stoichiometry. All that math. To be able to do stoichiometry, you must have a balance equation. We talked about this. A chemical equation is a recipe. For it to work, to be able to find out how much reactant do you need to produce so much product, or how much product can you produce if you have so much reactant, all of that only works if you have a balanced equation. Now, more things to remember. The coefficients, so the numbers here in front, these two, the one is implied, another two right here. These numbers right here that we used to talk about molecules. 2 hydrogens plus 1 oxygen gives you 2 molecules of water. And we said, okay, because we can double a recipe, we can do a dozen of the recipe, we can also do moles of recipe. We can call them moles. We learned this in the previous module. From now on, when we're doing stoichiometry, these coefficients, these numbers are moles. We read them as moles. They are never grams, they are never any other kind of mass unit. They are moles. Okay. And when we read a recipe, you need to follow the recipe and nothing else. Just follow the recipe. I have mentioned this in red several times, so I'm just going to mention it one more time because it's important before we get started doing stoichiometry for you to have this clear in your mind. A balanced equation is the same as a mathematical equation. So you can multiply, divide, you can do anything that you would do to an algebraic equation to this balanced equation, to this balanced chemical equation. Okay? So how does this work? We'll see in a minute. Now, the coefficients have a name. From now on, we're going to call them stoichiometric coefficients because we're doing stoichiometry with them. If you're following along, we are on page 175 in your textbook. So you need to know the definition and know that these little numbers right here are called stoichiometric coefficients. And they give you information in moles. Nothing else. Those are moles. 3 moles of hydrogen plus 1 mole of nitrogen gives you 2 moles of ammonia. Now, these little ones are called subscripts and just tells you how many atoms are in there. So 3 moles, each one of hydrogen has 2 atoms of hydrogen. The 1 is in parentheses here because usually you do not put a number 1. The 1 is implied. So have this very clear in your mind. Stoichiometric coefficients versus subscripts. Okay, let's look at an example. Page 164. it reads as follows, and then we're going to see how this is solved. A chemist forms ammonium sulfate, and they give you the formula, which is an excellent fertilizer, and they do that by combining ammonia, they give it to you also, the formula for the molecule, and sulfuric acid, also given to you. If the chemist ends up making 12.2 moles of ammonium sulfate, how many moles of ammonium were used? This is the kind of problems you're going to be able to solve in this module. Let's go to the board right here and let's see how this is solved. So I'm going to start by writing an equation, okay? And they said, let's see if I can get white here. Okay, my mouse. Okay. They said ammonia plus sulfuric acid, and this was given to you. You didn't have to write this on your own yet. Will give you that fertilizer, and they give you the formula as well. I'm just copying it right now, and then I'm going to talk for a minute about these parentheses right here, because I don't think you have been presented with those parentheses right this minute. Okay, when you have parentheses with something inside, it means that you have 2 of the whole molecule. So for example, here you would have 2 nitrogens and you would have 8 hydrogens, because it's 2 times 4, that's where the 8 would come from. And the 2 times 1, if there's nothing there, it means it's implied a 1, is the 2 nitrogens. So the 2 means you have 2 groups of this molecule. There's some molecules that mean that you need more than 1 of that kind. Okay, so there you go. You'll learn about this soon, but not yet. Just for right now, just know that the two is for everything inside the parentheses. Now, you wrote this. You just wrote this. Well, I wrote this, but if you were doing this at home, you'll be writing the formula yourself, and you know that it's not balanced because you just wrote it yourself. So the first thing we need to do is balance this. That's the next step, is balance the equation. Start counting atoms. 1 times 1 for the nitrogen equals 1. We said that here we had 1 times 2, because 1 inside, 2 of them equals 2. That is not a balance. So I'm going to put it in blue just so you can see. My stoichiometric coefficient right now that needs to be here is a 2. I may need to change it later, but right now we're going to put it 2. So it's 2 times 1 equals 2. It seems to be balanced. Let's do hydrogens next. Okay, hydrogen. 2 times 3 equals 6 for this side, and the hydrogen over here is 4 times 4 here times 2 equals 8. Well, that's going to be a problem in a minute. So oh, it's because I forgot to add those right here. Okay. So I forgot that there was hydrogen right here and also hydrogen right here. So I need to add those 2. So 1 times 2 for this other molecule equals to 2. And now I have my 8. Okay, that makes sense. So now it's balanced. That's great. Let's move on. Make sure that the next one is also balanced. What do we have left? The sulfur. So 1 times 1 equals 1. And on this side, the sulfur is 1 times 1 equals 1. Perfect. Oxygen only here present, so is 1 times 4 equals 4. And on this side is 1 times 4 equals 4. Okay, so now it's balanced. Let me erase these. And I said to you, it was very, very important for you to have a balanced chemical equation. For it to be a recipe, it does need to be balanced. Okay, so let's see if I can erase this. No, I think it's too big. The eraser doesn't seem to be working very well. Okay. Anyway, now that we have a chemical equation, we can start working. The problem said that we had 12.2 moles of ammonium sulfate. And they wanted to know how many moles of ammonia were needed to create it. So this right here, okay, the amount that we have is 12.2 moles. Okay, and they want to know how much ammonia was used. This is the ammonia right here. They don't know how much ammonia. So we're going to use stoichiometry. We're going to use stoichiometry to solve this. The first thing you need to do is to read the recipe. The two things that we need to connect are these two things right here, the ammonia and the fertilizer. Okay. So what does it say here in the recipe? It says 2 moles of ammonia will produce 1 mole of the fertilizer. So let's write this down. 2 moles of the ammonia will produce 1 mole of the fertilizer. I'm not going to put the 1 there, although you could if you want to, but it's not done. Okay. This is how they are related, those two things. This is the factor that relates the two things. We're going to be using this to do stoichiometry. Now, anytime that you have a problem like this, you start with whatever they give you. So let's see if I can get another page. Here in the other page, I'm going to start with what they gave me. 12.2 moles of it's not writing very well. Let me see. Of the fertilizer. Okay. I open my factor label method because I'm going from one thing to another. And I say to myself, what am I trying to get rid of? What is that I don't want anymore? I want to have moles of ammonia, not the moles of the fertilizer. So I'm going to put the moles of fertilizer at the bottom. And here we go. It takes time to write things sometimes. But you have to do what you have to do. And we want to end with the moles of ammonia that were needed to produce this much fertilizer. And 3. Okay. If you remember, according to the formula, 2 moles of ammonia will produce 1 mole of the fertilizer. I'm going to write it in blue. I write this. I wrote it in the previous page, but I guess I should write it again. So 2 moles of the ammonia will produce 1 mole of this fertilizer. Okay, this is the information that I read from the recipe. So now I need to make sure that I'm putting the moles, the number of moles, in the correct position. So the ammonia, where is, I copied this, is supposed to be 3. Okay, the 2 goes here and the 1 goes here. 2 is accompanying the ammonia, so it needs to go with the ammonia. The 1 was with the fertilizer, so 1 in the fertilizer. Now I do the math. 12.2 multiplying by 2 divided by 1. That doesn't change anymore anything. So if I do the math, putting it all in the in the calculator, it comes out to 24.4 moles of ammonia. This is your answer. I used the recipe to know how much ammonia I would need if I wanted to produce 12.2 moles of the fertilizer. Okay, so let's go back to instruction. Let's see. Okay, let's talk about limiting reactant. It should make sense that if you run out of one of the reactants, the reaction will stop. You can produce as much product as the reactants allowed you to produce. So whichever reactant you run out of first becomes your limiting reactant. It limits the reaction. And here's an example with food. Okay? If you're trying to make scrambled eggs, and you need 3 eggs, 2 tablespoons of milk, and a pinch of salt, and 1 tablespoon of butter. What happens if you want to make this recipe, but you run out of eggs? You have plenty of butter right here. You see, you have more than 1 tablespoon. Here in this picture, you have plenty of milk, and it looks like you have a lot of salt. But the recipe says you need 3 eggs. And these are the amounts of things. That means once you have used these 3 eggs, it doesn't matter how much butter, how much milk, how much salt you have left. You only will be able to do 1 serving of the scrambled eggs recipe. So the eggs have become the limiting factor here. And the same is true for chemical reactions. If you run out of one of the reactants, it will stop the reaction. Okay, here we go. Another example. What is the limiting reactant if 70 moles of hydrochloric acid are reacted with 1 mole of potassium dichromate in the following reaction? So they give you the reaction. This is already being balanced for you. So it says that you need 14 of this hydrochloric acid. You need just the 1 here with the potassium dichromate, and you'll be producing 2, 2, 3, and 7. Those are moles. And now they're saying that if you have 17 of those moles, and you only have 1 mole of these, which will become the limiting reactant. Well, what happens here? If you only have the 1 and you need 1, you're going to be left with 0. If you started with 17 but you only needed 14, you're going to be left with 3. These 3 cannot do anything else. There's no more of the second reactant to produce more product. The potassium dichromate has become the limiting reactant because it's gone. If it's gone, it cannot combine with the hydrochloric acid to produce anything else. Okay, that's the idea behind limiting reactant. Okay, you are going to be doing experiment 6.1 on page 166, in which you're going to be trying to find out the limiting reactant. Okay, remember to ask questions next time that we meet before you turn in the lab report. If you have questions, just email me. Let me move this a tiny bit right here. Okay. Fully analyzing chemical equations, page 168. When all reactants are added in the right quantities necessary and we don't have leftovers, everything gets used up to form product. And we say that the reactants reacted completely. In the previous one, okay, let's see. Maybe I should go a tiny bit more about this. Okay, this was the limiting reactant because it was gone, but you had leftovers. The hydrochloric acid right here, you had 3 moles still left. They were not able to do anything, but they were leftovers. So it was not completely reacted. Okay, let's look at this one for a second. It says, what is the limiting reactant now if you have 40 moles of the hydrochloric acid and 3 moles here of potassium dichromate? Okay, let's look at this for a second. For each one, you need 14 of these. So you have 3 times 14 is 42. You need 42 for all 3 to be able to be used. That means that you still needed 2 more to be able to use all 3. So now this one has become the limiting reactant. The hydrochloric acid has become the limiting reactant. You have plenty of this reactant, but according to the recipe, each mole requires 14 to be able to continue to produce this product. And you had 3 times 14, to see how much you need, is 42. So you were short 2 moles. Now, on this one, what is the limiting reactant if 20 moles of hydrochloric acid are reacted with 2 moles of potassium dichromate in the following reaction? Okay. So the recipe tells you 2, 1. 2, 1 produces 2, 2, 3, 7. That's the recipe. I mean, that cannot change. But now they say that you have 20 of these and you only have 2 of these. 2 of them requires 28. See, because each one requires 14. 2 will be 28. Now you are short 8 moles for the whole potassium dichromate to be able to be used up. If you want to use all of it, you need 28 and you don't have them. So the hydrochloric acid continues to be your limiting reactant. I hope this makes sense. So whomever runs out first is the limiting reactant. If both of them were 0, then it would be perfect. All of the reactant would be used up to produce the maximum amount of product that they can produce. So if that happens, if you don't have any leftovers, then you say that the reaction has reacted completely. Okay, let's do example 6.2 on page 169. So it reads as follows. The antacid tablet Tums with an active ingredient of calcium carbonate neutralizes excess hydrochloric acid in your stomach according to the following reaction. They are giving you a balanced chemical equation, so if it's given to you, you don't have to worry about balancing it. It's already balanced. If 0.075 moles of calcium carbonate are in a Tums tablet, how many moles of the hydrochloric acid can it neutralize? When it neutralizes that amount of stomach acid, how much calcium chloride and water and carbon dioxide are produced? So there are several questions here that you're going to have to answer. Let's go to the board for a second and see how we tackle problems like these. I'm going to copy the reaction, so I have it right here. Let me get white. So I start with my calcium carbonate, and I'm not going to put the solid state here, just to save some writing and space. 2 hydrochloric acids, or aqueous. AQ is for aqueous, meaning water. You're going to see this a little bit later. So we have the calcium chloride, also aqueous, and the water, which is a liquid, and the carbon dioxide in a gas form. Okay, this is given to you. It's already balanced, so it's already a recipe. The first question says, how much 0.0075 moles of this calcium carbonate, how much hydrochloric acid it can neutralize. Okay, so they want to know how much of these will be reacting with 0.075 moles. That's the question. So we need to relate those two reactants. How are they related? According to the formula. The formula says that 1 mole of calcium carbonate will react with 2 moles of hydrochloric acid. That's how the recipe reads. That's what it says. Okay, nothing here means 1. It's implied. So for each mole of calcium carbonate, you can neutralize 2 moles of hydrochloric acid. But of course, we do not have a whole mole. We have 0.0075 moles in one tablet. So we always start with whatever they are giving us. 0.0075 moles of that calcium carbonate. We open our fraction and put at the bottom what we're trying to get rid of. We don't want moles of calcium carbonate. What we want is to know how many moles of hydrochloric acid it can neutralize. Let's read how they are related to one another according to the formula. 1 to 2. Make sure that you put the numbers in the right place. The 1 goes with the calcium carbonate, so we're going to put 1 right here. The 2 goes, I forgot to put moles here, moles. 2 goes with the hydrochloric acid. So make sure that you put it in the right spot. Do the math, and if you do the math, it says that 0.015 moles of hydrochloric acid were neutralized when we took one of those tablets with 0.0075 moles of calcium carbonate. So the first question has been answered. Let me erase this so we have some more space here. Now they want to know how much product is being produced when you have 0.075 moles and you neutralize that amount that we just found out, 0.015 moles of hydrochloric acid. So how much of the product is produced when that happens? So what we're doing now is relate this to each one of them. They want to know each one of them. I hope you see that is 1 to 1. Nothing is going to change, but we're going to do the math anyway, so you can see what we're talking about. Let's start by relating the calcium carbonate with the calcium chloride. So according to the formula, the recipe says that 1 mole of calcium carbonate will produce 1 mole of this calcium chloride. So that's just reading the formula. Now I'll start with what they give me. My calcium carbonate, I open my fraction, I put at the bottom what I'm trying to get rid of. So moles of the calcium carbonate. I want to end with the calcium chloride. So with moles. So what does it say here? 1 to 1. We are gonna go like this and do the math, and you see that that doesn't change anything. You're gonna have the same amount. I think I forgot a 0. Yeah, moles of calcium chloride. So you produce this much calcium chloride. Now let's erase some of these so we can do the next one. All of them are 1, so it's not going to change anything, but I'm going to show it to you so you can see that that is true. I'm going to wait a tiny bit more cleaning up here. So how are they related now? This one is done. We're doing the second one. We're trying to find out how much water we're producing. So according to the table, the reaction right here, the recipe, is 1 to 1 as well. So 1 mole of water. Each mole of calcium carbonate will produce 1 mole of water. So you start with what they gave you. I should not have erased these. Now I have to write it again. So calcium carbonate. So the math is not very complicated, but there's a lot of writing. And here we have the moles of calcium carbonate that we're trying to get rid of, and we're going to end with moles of water. 1 to 1, so 1 to 1. Do the math, it's the same number. Moles of the water. So there you go. This is done too. We just done this as well. I'm going to leave this part the same. I'm just going to erase this because we always start with the same. And I'm going to erase these because that's what's changing. And change say glue. Make sure that I got it. This has been done. Now we're trying to calculate the amount of carbon dioxide that we are producing here. So 1 to 1 again. So moles of carbon dioxide. Open your fraction, your moles of calcium carbonate at the bottom, so you can cross it like this, and your moles of carbon dioxide at the top. 1 to 1, 1 to 1, it means it's the same number. 0.0075 moles of your carbon dioxide. And now this is solved. It's not always going to be this easy. It's not always going to be 1 to 1. Sometimes it's a different coefficient in the front, so you need to do the math then. But in this case, it was 1 to 1, and it didn't change anything. So let's erase the whole thing, and let's go back to instruction for a second. So if you have questions about this, ask. Let me clear these, go back to instruction, and let's move on. But what we're doing, all these relating things inside the chemical equation, all the math we're doing, all of that is called stoichiometry. That's all it is. Stoichiometry is the math that you can do with a chemical equation to relate products with reactants. If you have the limiting reactant, to know how much product you can make, and so on. All of it is stoichiometry. So let's move to the next one. Page 170. So we're plodding along. It says relating products to reactants in chemical reactions. Chemists use stoichiometry to determine the quantity of a reactant necessary to make a certain amount of product. Balanced chemical equations or reactions are recipes and show the minimum amounts necessary. So it's just repeating it and repeating it and repeating it, because we still have several modules to go, and you're going to be doing stoichiometry for most of them. So let's read this recipe. What does it say here? 2 plus 4 plus 1 will make 2, and 2 of these and 2 of these. That's all it says. The stoichiometric coefficients here in the front. Nothing means 1. Is what you need for the reactants, and these are the things that are being produced. That's how you read it. Okay. Example 6.3 on page 170. So there's a lot of repetition in this module, but it's so important. That's why he repeated so many times. Let's see. A chemist wants to make either... Did I copy that right? This is a 10 right here. This is a 10, and that's the oxygen. Okay. So it's trying to make is a medical anesthetic, and here's the formula. The chemist uses the following reaction, and the reaction is given to you. That means it's been balanced. Yay, you don't have to balance it. If the chemist needs 134.9 moles of ether, okay, what is the minimum number of moles of this reactant and of the sulfuric acid here that he needs? How do we solve this? Well, stoichiometry is going to come to the rescue. Okay, let's get the whiteboard and see how this is solved. I'm going to start by writing the recipe so I can read afterwards. And you're going to have to wait for me to copy it, because it takes a tiny bit of time. I don't have them ready. Plus the sulfuric acid here yields the ether. This is the ether. We have not yet learned how to read all this stuff. That's fine. And notice that I'm not putting the states of the matter. I'm not putting gas or liquids or anything like that, just to go faster. And okay, so this is my recipe. This is a 5. Okay, so this is the ether. I'm gonna put it here. Ether. Okay, So what did the problem say? If the chemist needs 134.9 moles of ether, so he wants 134.9 moles. That's what he wants of ether, okay? He wants this amount. What is the minimum number of moles of these right here? How many moles will he need to be able to create this amount of ether? And then also, how many of these he will need? There are two parts to this question, so we'll tackle one at a time. We'll start with the first reactant, and I read the recipe. According to the recipe, if I connect this one to this one, I'm going to put it in different colors. The recipe says that 2 moles of this reactant will produce 1 mole of ether. Okay. This is in the recipe. 2 to 1. Remember, there's nothing here, it means 1. So now I can do the math for that. I'll start always with whatever they give me. It doesn't matter if you go forward or you go backwards. Stoichiometry allows you to go from one side to another. It doesn't matter. This yielding is like having an equal sign right here. So you can read it backwards if you want to. So if I want to produce 134.9 moles of ether, I use my factor level method. I know that I don't want moles of ether. That's what they are giving me. What I want to know is how many moles of this reactant I'll need. So I'll put it at the top. This gets crossed, you already know that. But then I need to make sure that I put the numbers in the right place. So where is this? This is here at the top. So the 2 goes at the top. And this right here is at, did I copy it wrong? No, it's supposed to be a 1. Yeah. Okay. So the 1 goes at the bottom. Okay. So do the math. Multiply the 134 times 9 by 2, and you'll see that you would need 269.8 moles of the reactant, of the first reactant, to be able to produce the 134.9 moles of ether. So the first one is done. Let's do number 2, second part of the problem. So now we're trying to, let's see, I'm going to do it in red. I'm trying to relate this second reactant to the ether. So we're still doing ether, okay? And according to my recipe, 1 mole of this acid is needed to be able to produce 1 mole of this ether. That's what the recipe says. 1, there's nothing here, is 1 to 1. So you start with, I know it's not going to change anything, but we're going to do the math anyway. So 134.9 moles of what? Of our ether, because that's what they give us. Factor level method, trying to get rid of those because we already have that information. What we need is the amount of the second reactant of that acid. So here you go. And now 1 to 1. There's nothing to think about here because it's 1 to 1. So it's the same amount, 134.9 moles of the second reactant are needed to be able to produce 134.9 moles of ether. So what are we learning in this second example? We're learning that it doesn't matter how you read the recipe, forward, backwards, things are related. You can put an equal sign. It's a recipe, okay? That's what you can do with it. So let's clear these and let's go back to instruction. Okay. Using chemical equations when the limiting reactant is identified. Sometimes they will tell you that one of the reactants is limiting. And then what do? Well, sometimes chemists add lots of an extra cheap reactant to make sure the more expensive reactant becomes the limiting reactant. That means it's all used up. That should make sense. If something is very, very expensive, you want to use it up. You don't want that you don't want leftovers for that very expensive reactant. So they do it on purpose. For example, here. This right here has silver. This is silver. This is very, very expensive. The hydrochloric acid is not. So the chemist wants all of it to react. To make sure that all of it reacts, the chemist will put a lot of hydrochloric acid. So this one will run out before you run out of the hydrochloric acid. And all of it will be used up to produce as much of the products as you can. And chemists will do that on purpose. When you do that, we talk about excess reactant. This one right here, the one that they added so much that it will never run out because, well, it will eventually run out, but it will not run out before the more expensive one will run out, is called excessive reactant because it's an excess. It has a lot of it. So this becomes the limiting reactant, and this is the excess reactant. I hope that makes sense. Okay. How does this work? Let's apply these to a problem. Page 172 in your book. Some ores contain a small amount of precious metals that are in compounds with many other elements. For example, one common ore found on Earth is this one right here. And you see the silver right there? That's a precious metal. Since silver is a precious metal, it's useful to be able to extract silver from this ore. And this is the reaction that allows you to do that. Okay. So it's being combined, this ore is combined with zinc, and here's the silver by itself, plus other products. It says, if a chemist adds, so basically let's talk about for a minute about limiting and excess reactant. You want this to be the limiting reactant. You want all of it to be used up. You want all that silver extracted. You want this to be your excess reactant. You don't want to run out of these, because if you run out of one, it stops the reaction. And if you run out of these before you run out of this one, not all the silver will be extracted. Now, as a chemist, you can do that. You can put excess of one of the reactants to make sure that the other one limits the reaction, that you run out of it. If a chemist adds 5.61 moles of this ore to excess zinc, that's what you want, excess zinc, you just want to have plenty. How much pure silver, which is right here, can be made? Okay. Let's go and solve these. And let me copy the recipe. It is a recipe in white. So here's our ore. Here's our silver that we want to extract. Carbon 2 and nitrogen plus the zinc, which is in excess, and that will produce 2 moles of the silver that we're trying to look for, plus another zinc compound here, and another compound, 2 of these. Okay, so that's the formula that they gave us. We also know that this one right here is excess reactant. They told us that. That right there indicates that this is the limiting reactant. This is the one that will limit the reaction. When it's gone, it'll stop the reaction. Okay. So what else did they tell us? They told us that we started with 5.61 moles of the ore. That's what we have, okay? That's what we have. That's how much ore we have. And they want to know how much silver you can produce. So how much silver you can produce. Let's read the recipe. What does the recipe say? The recipe says that 2 moles of the ore, see those 2 right there, the 2, will produce 2 of silver. That's what the recipe says. I read the recipe, I know how they are related, and now I can do stoichiometry, can do some math. Start with the number they give you. And the math is not very difficult. You take more time writing things, the formulas, than anything else here. Open your factor level method. You know, you want to get rid of those moles of the ore. And end with moles of silver. And there's not much thinking here because it's 2 to 2, so it doesn't matter where you put the 2 or the other 2. But if you need to read the recipe, if there were different numbers, you need to pay attention what number accompanies each one of them. So the 2 with this one would be here, this 2 with argent with silver will be here. Okay, so what's the math? The same amount. Okay, 5.61 moles of the silver, because that's like 1. Okay, so that's it. That's how you use the concept of excess reactant versus limiting reactant. If they tell you that one is in excess, you know the other one is the limiting, and the limiting is the one that will stop the reaction. Once it runs out, it runs out. You cannot produce any more products. Okay, let me clear this for a second and go back to the last part of instruction. Okay, now volume relationships for gases in chemical equations. The stoichiometric coefficient, so those numbers, the 3, the one that's implied, and the 2, we said they were moles. But, and it's true, they're always moles. But if you're working with gases, you see the G here stands for, oops, I went too far. Let me go back for a minute. Okay. I can find it right here. Okay. So the G stands for the gas, so the state of that hydrogen, nitrogen, and the ammonia right here is in the gas format. If you are dealing with gases, the stoichiometric coefficients in that chemical equation can stand for units of volume. Gay-Lussac's law. That's Gay-Lussac's law. Gay-Lussac is a French chemist that came up with this law. I mean, when I say came up, when I use the word came up, doesn't mean he just took it out of thin air. He was doing experiments and studying this, and he discovered this to be true. So the stoichiometric coefficients in a chemical equation relates to volumes of gases in the equation as well as the number of moles of the substances in the equations. This law can only be used in stoichiometry if everything you're trying to relate is a gas. So you only use this law to relate gases. For example, you have 1, 2, and 1. They're always moles. You always can relate things inside the equation in the recipe as moles. This case is not a problem because everything is a gas here. So you could relate this reactant with this product, those 2 reactants, this reactant with this product. All of it could be some unit of volume. In this case is the liter, because that's what we are using. That's the metric system. Okay, so you could use stoichiometry here and calculate the amount of liters of this product given a certain amount of liters for this reactant by using the coefficients here in the front, because everybody here is a gas. Let's look at this one right here. This is a solid, this is a gas, this is a solid, and this is a gas. So this law, the Gay-Lussac law, only works for gases. The only thing you could relate here using this law, so calculating volume in liters, would be the hydrochloric acid and the water. You cannot do this solid with this gas, or this gas with this solid, or this gas with this solid, and call it liters or any other unit of volume. It doesn't work that way. It only can relate gases to gases if you want to use volume units. Okay, we'll see how this works in a minute. For example, this is the last example we do on page 175. It says a car engine burns gaseous octane, and they give you the formula. If a car completely combusts 12 liters, that's a unit of volume, of gaseous octane in excess oxygen, how many liters of carbon dioxide will be produced? So they're asking you for liters as well. Another is the unit of volume again. So how do we solve these? Okay. We start by writing a recipe. Let's start with, let me get a white. I like to start with white. I don't mind changing colors afterwards, but I like to start with white. So here is what they give us. We know that this is a gas. They said it was burning. Burning is a combustion, so we know that we are combining with oxygen, which is another gas. And we're producing carbon dioxide, which is another gas, and water is going to be also in the gas state. I know it's going to be in the gas state because it's a combustion. It's a big explosion, so it's so hot that it will be in the gas state just because of the amount of energy that's being released. I wrote this. I know it's not balanced. So the first thing I need to do is to balance this equation. Okay, so I'm going to put my little line here and start counting atoms. So carbon, 1 times 8 equals 8. Carbon, 1 times 1 equals 1. That's not gonna go very well. I'm gonna try to put an 8 here. I mean, you need to start someplace, so 8. 8 times 1 equals 8 seems to be okay for right now. Okay, let's keep going. Leave the oxygen for last. So hydrogen, 1 times 18 equals 18. Hydrogen, 1 times 2 equals 2. That's not going to go well either. So I need a 9 right here for right now. 9. 9 times 2 equals my 9. Sorry. 18. Okay, pay attention, Miss Monica. Okay, so now we have our oxygen. Oxygen 1 times 2 equals 2. And my oxygen right here is, I have it two places, okay? I have the 8 times 2 equals 16. And I also have it here. So my 9 times 1 equals 9. Well, I already see that it's not gonna work. Let's add them up for a minute. So I have, seems to be having 15. Am I doing this right? I mean 25. I don't know why I said that. 25. Okay, so 25. So remember to use your fractions then. It is just like bizarre. There's no way to reconcile it. So if I need 25 here. So I have 25 halves times 2. It will be the 25 that I need. Okay. So that is balanced, but it has a fraction. So I know I can leave it like that. So my next step is make more room. Dun, dun, dun. And then get rid of my fraction by multiplying by 2 everything. So I'm going to end with 2. Remember to put gases here because only gases can be related in units of volume, so I need to know who is a gas. Although everybody's a gas here, in other instances it may not be so. So 25 and the oxygen to yield 16 of carbon dioxide plus 18 of water. This is a gas, and this is a gas, and this is a gas. Okay, now I have a recipe. After I balanced it, I have a recipe. Now I can do stoichiometry and relate things. What do they want from me? Let's read it again. It says, if a car completely combusts 12 liters of gaseous octane, so 12 liters. Let's get a different color. So I have 12 liters of this octane gas. It says in excess oxygen, so I'm not going to run out of this. This is excess reactant. That means this is going to be my limiting reactant. Okay? This is the one that will limit the reaction. How many liters of carbon dioxide will be produced? So they want to know this. How many liters of carbon dioxide? Can I use liters here? Yeah, I can, because this is a gas and this is a gas. And the Gay-Lussac law says that if I have gases, I can use my stoichiometric coefficients to calculate volume. So what does it say in my recipe? My recipe says that 2 liters of octane gas will produce 16 liters of carbon dioxide. This is what my recipe says. 2 to 16. You see that? Now, I'm gonna erase this because I need more room. Take this out and I'll start at the bottom with a different color of the blue. So I'll start with the 12 liters. Oops, what happened here? Okay, let's see. Okay. 12 liters of the octane gas. I'm going to open my fact level method. I want to get rid of my liters of the octane. I'm having a lot of problems with my mouse. I don't understand why, but it is what it is. So liters of my octane gas and end with the liters of carbon dioxide. That's what I want. I want to be able to do this. Well, read the recipe. 2 of the octane, 2 here, 16 of the carbon dioxide, so 16 of the carbon dioxide, and this is just math. Multiply 12 times 16 divided by 2, and this computation comes up to 96 liters of carbon dioxide. 96 96 that was a 96. 96 liters of carbon dioxide is how much you can produce if you start with 12 liters of the octane gas. But remember, you only can do that. You can only calculate liters or units of volume if you're relating gases, one gas to another gas only. So you're going to have several on your own to do this week, and this completes instruction for the first half of module 6.